Let's take a look. Let's play a little bit. Whoa, I don't know what just happened there. Ghost in the machine. Let's take a look at a couple more functions, the relationship between a function and its derivative. So let's just get crazy here for a sec. Yeah, let's do this guy right here. All right, and see what happens. Now, this is going to be f of x. Let's just try to visualize what's going to happen if we try and sketch its derivative. Well, if this is f of x, for me, the place that I always look is where f of x levels off. So f of x levels off there, which means, think about it, its tangent line is going to have a slope of 0, which means its first derivative, this guy, remember, the end result here is we're going to try and sketch what f prime of x looks like. Wherever f of x levels off, the slope of its tangent line is 0, which implies that the first derivative has an x-intercept. Again here, so x-intercept. Again here, x-intercept. Now, look at this. The slopes of these lines tangent are all positive, and then they get a little smaller and a little smaller and a little smaller, and then they level off, right? Which means positive, big, right? And then we come down here and we hit our our x-intercept, right? Now, what happens beyond that? We'll check it out. Look at the slopes of my tangent lines. Now they're negative, negative, steep negative, so big negative, and then they start to level off. So what happens is I get this. These are all negative because the slopes of these tangent lines are all negative. Slopes of these tangent lines all positive, and then they level off back towards 0. So that means that the first derivative is going to be positive, and then head back towards 0. And then for the rest of the ball game, look at what I got here. I have tangent lines that are all negative, which means that this guy goes down here, which means that this is a rough sketch of the first derivative of f of x. Now, you ready? Whoa, pen's not behaving itself. Let's talk about what it means to be differentiable. We say f of x is differentiable at x equals a if it has a derivative at x equals a. Now, this really begs the question. When is f of x not differentiable? In other words, differentiable. And there are three really important cases, and we'll discuss all three of them. So you ready? Let's go case 1. So we're going to go case 1. Case 1 is simple. Think about this. Let's say that I have a function that's cruising along, and then all of a sudden, whoop, it pops up here. All right? If my limits aren't the same at some point x equals a, then when I do the whole limit as x approaches a of who cares, I'm dead. Remember, if this is f of x, f primed of x has to be a function, is a function. I'll just call it a func. So if I'm getting two separate limit values, then I'm dead. Now this really begs the question, what's wrong with this function? And there's really nothing wrong with the function, but what do we know, what type of function is this? Or more importantly, what isn't it? It's not continuous. So what we have is a theorem that falls out of this, and the theorem simply says if f of x is differentiable, and I'm going to diffable at x equals a, then f of x, whoops, did I write f prime of x? Sorry guys, I meant to write f of x. If f of x is differentiable at x equals a, then f of x must be continuous. It's got no choice, okay? It has to be continuous because how do we find a derivative? We take a limit. And if we take a limit at something that's not continuous, then the limit doesn't exist. You see how that all ties into each other? Now, there's something that's really important here that you have to understand. Check this out. If if f primed of x exists. According to this theorem right up here, this implies f of x, the function, f of x is continuous. Well, what does this imply? This implies the limits of f of x exist. All right? However, the converse is not true. In other words, if the limit exists, we know from experience. Does this imply that it's continuous? Absolutely not. Remember, I could have a function that looks like this. Now, I can't take a derivative at this point because the function doesn't exist there. It has no tangent line, right? However, the limit exists. I know that the limit as x approaches a of f of x equals some L. However, it's not continuous, and therefore it's not diffable. Now, if you know that it's differentiable, that means that the derivative exists. You get all of these for free, which is pretty cool. All right, let's talk about the other cases. Let's talk about case 2. Case 2 is if you have a function that looks like this. Let's say you've got this function right here, and this is the point x equals a. Now, here's the problem. Remember, the derivative of a function, this is going to be my f of x. The derivative of a function has to be a function, all right? So look close. If this is my tangent line, okay, cool, that looks oh, wait. But what about if I approach from the left-hand side, or excuse me, from the right-hand side? Now I have two tangent lines, which means I have two slopes of two tangent lines, which means that f primed of a can equal two numbers, right? So in other words, you stick a into f primed, and out pops these two numbers. I violate my vertical line test. I'm dead. This right here is called a cusp. Sometimes you'll hear it referred to also as a corner. Corners, these create points of non-differentiability, and you have to be very, very respectful of them. Okay? Let me change back to blue. We'll play with these some more in class. I just want to give you the intro. Okay? Let's look at case 3. Oops, case 3. Case 3 is most easily exemplified by y equals the cube root of x. Can you visualize that sucker in your brain? It looks like this. All right? This here is f of x. The problem is, at x equals 0, guess what I have? I have a vertical tangent line. And we know that the slope of the tangent line, when it's vertical, doesn't exist. Therefore, it's technically not differentiable at that point. In other words, when I stick in a value, when I stick x equals 0 into f primed of x, I get a value that doesn't exist. All right? So these are really the three cases where you get points of non-differentiability. All right? If a function doesn't have any cusps, if it's continuous, if it doesn't have any vertical asymptotes, we're golden. You can take derivatives everywhere. Okay? One last quick little thing, and then we'll be done with this section. Okay? And I want to talk about the different notations for f primed of x. So different, because it's really a language, different notations. And you have to understand that this idea of derivatives got sent out to a whole bunch of different mathematicians, and they came up with all sorts of different ways of talking about derivatives. Okay? So different notations for f primed of x. All right, first things first. We got f primed x. That's kind of the standard because we're real comfortable with f of x. Another way is y primed of x, or just y prime. You'll see it both ways. Now the last way is the most compelling, and it's actually the most useful because it's algebraically created. A guy by the name of Leibniz came up with a notation. And what this term right here says is it's an algebraic way, and you'll see when this pops out in just a sec. It's an algebraic way of saying take the derivative. That's all that this really says right here. Now think of this not as some weird notational thing, but as an algebraic construct. When we're done, we end up with dy over dx, which, if you look at this, doesn't this look very much like delta y over delta x, right? They're really similar. This is the geometric construct for slope. This is the Leibniz construct for derivatives. Now, what these mean are really small change, as opposed to who cares, just any change. All right, remember, teeny tiny, when we take the limit, we're talking about really small change, really small, oops, really small change. Okay, this is small change. All right, now this notation, this Leibniz notation, is going to pop up again and again. Now, if I can take a derivative of a function, and that derivative is a function, guess what else I can do? I can take its derivative. All right, so I can express that as f double primed of x. I can express it as y double primed of x, or y prime, or I can go through this exact same process here, and we won't have to do this anymore, of dy over dx, and watch what I get. Now, this notation is a little cumbersome, so you're going to have to bear with me. I end up with d squared y over dx squared. Now, we don't put this in parentheses, which we should, because it takes up too much typeset. Back in the day, they had to set print by hand, and if I wanted to throw parentheses into my writing, then I would have to set the type for that, and that would be a pain in the butt. Now, the thing that I want to really emphasize about higher order derivatives, second derivatives, third derivatives, etc., is that, think about it this way. F prime double primed of x gives, and this will be my mantra, the exact same type of information about f primed of x as f primed of x gives about f of x. Now, I'm just going to plant that seed, and I'm going to let that grow, and we'll talk about that over and over and over again, because that may seem a little bit nebulous right now, but it really is an amazing piece of information. All right, I hope you enjoyed the lecture, and I'll see you in class tomorrow. Have a great day.